Hi guys, this is Dr. Edwards. I want to give you some pointers here on solving problem 2.112 of Griffith's book. And so if you've been assigned this problem, the portion I'm going to do will help in that methodology. Find the expectation value of x, the expectation value of p sub x, the expectation value of x squared, the expectation value of p sub x squared, and the expectation value of the kinetic energy for the nth stationary state of the harmonic oscillator using the method of example 2.5. And then once you've calculated those, you check that the uncertainty principle is satisfied, that the uncertainty in the position x times the uncertainty in the momentum p is always greater than or equal to h bar over 2. Okay, so I'm going to do the uncertainty in x squared, and I will want you to do all the other parts, including the uncertainty in x squared, and turn this in as your homework problem. Firstly, though, let me go back and review example problem 2.5. It's on page 49 of Griffith's book. In this example, find the expectation value of the potential energy of the ith state of the harmonic oscillator. And it's written thusly. The expectation value of the potential energy V is equal to the expectation value of 1/2 m omega squared x squared. Now the mass of the oscillator is known, and the angular momentum is also known, and they are mere constants, so you can take them out in front of the integral. So the integral that has to be done for the harmonic oscillator set of wave function is the integral from negative infinity to positive infinity of psi sub n star with x squared sandwich in between psi sub n dx. Okay. Now, how to configure the integrand in order to find the expectation value? You need now to recall that the operator for x is given in terms of the raising operator a sub plus and the lowering operator a sub negative. And the momentum operator p is given in terms of the imaginary number I and the raising operator and the lowering operator, okay? So with x given as this term, in this example, since you need to have x squared, it is finally given as this expression. Let me show you on the next page how I've attained that. Okay, so I start with the definition of x, operator written in terms of the raising and lowering operator. I write p just to have completeness, but I'm not going to use it here. So now x squared as an operator then is the product of the x operator. It is important to keep the order of all operators. Do not interchange the order. So I'm going to use the for rule here. When I multiply just the constants, I get h bar squared over 2m times omega. And then a sub plus times a sub plus is the product of a sub plus, and a sub plus times a minus is a sub plus times a minus, and a minus times a plus is a minus times a plus, and then a minus times a minus is a minus times a minus. So that's what you have. And you can write it then in better looking form. This is really a sub positive squared, a sub positive times a negative, a sub negative times a positive, plus a sub negative squared. So now you can use this back in the example that we're working on. So you come here, you bring this and put it into the expression there for x squared. So when you do that, the expectation value of v becomes h bar times omega over 4. This 1/2 times that 1/2 gives you the 1/4. The integral then of psi sub n star times the quantity of these operators in between. Now, how do you make these calculations? Let me have you recall as well as I have shown here. Where do I show that? Right here. That a sub plus squared on the own sides of n is the square root of the quantity size of n plus 1 times the size of n plus 2, and you get psi sub n plus 2. This is a raising operator, so it raised psi sub n to the next sister wave function n plus 2. This is both now the lowering times the raising on psi n gives you just psi n times psi n. It gives you n times psi sub n. Now the raising times the lowering in that order on psi n gives you the quantity psi n plus 1 times psi n. And then two consecutives, a negative on psi sub n, gives you the square root of the quantity n minus 1 times n, psi sub n minus 2. I also want you to just recall that these are base set of functions. I call them sister functions just to show that they are connected with each other. And with these basic functions, it is always true that the integral of one of them, psi sub n star of x times psi sub m of x dx, is equal to 0 when m does not equal to n, when the subscripts for the functions are not the same, and it's equal to 1 when the subscripts are the same. So with these in hand, you can come back now and see how to find this expression right here. Let's see, where did I do it? Back here. So you put those quantities in, you go through the steps. Let me see, I go through the steps for you here. Okay. And it turns out that these are the same part of the steps for problem 212. So you can then find the uncertainty in x squared. You write it out. The integral of the sum is the sum of the integrals, as I have here. And recall that. You put those in, and then you can find the expectation value of x squared here in these terms. You have this expression here. You have this one. You have that one, and you have that one. These two are going to go to 0. Let's see, where do I show that? Right here. Here. This one goes to 0 because it's the integral of psi sub n star psi sub n plus 2. They are not the same. But this one does not go to 0. It's going to give you 1. That one does not go to 0. It gives you 1. But this one goes to 0. So you're left, when you find the expectation value of x squared, you're left with finding that the results of finding the expectation value of x squared is given as this quantity here. H bar squared times the mass of the oscillator times the frequency to the nth power. I'm sorry, n plus 1/2, where n is the order, the number for that particular state. Okay, so that's what I want you to do here. So let me see. I have shown you how to find the expectation value of x squared. You will find the expectation value of x. You come here, you take the value of x, you follow the same method as in this problem here, but as opposed to x squared, you will have x, and then you put that quantity there in sandwich in between, and you let the operator a plus operate on psi n. You let a negative operate on psi n, and you get two expressions, and you can perform the integration. All right. I hope this helps some for your being able to solve problem 2.12. And then once you get each of these, you can then figure out the uncertainty principle. You can calculate the uncertainty, and it had better come out to be that h bar over that delta x times delta p is always greater than h bar over 2. Okay, that's all I wanted to share with you on this problem. Get busy and solve this homework problem 2.12 and turn it in. Have a good day.